So good morning, everyone, and let's see if we can get going here. So, following up on what we covered on Monday, then today we're going to talk about some practical experiences in terms of assessment and what people do to determine whether or not there is a risk of a failure, of an accident, or potential contamination. So this first talk, this first hour, is going to be related to an uranium mining project in Virginia, which is a state in the US, where around 2010, the cost, the economics of exploiting uranium, mining uranium again, and the cost of production became economically attractive. And there was a number of dams, sorry, a number of dams in the system, but there was an area in the state of Virginia where there have been a number of former uranium mining leases. These were areas that before they had been exploited for uranium and then became very, very expensive to continue to do that. So they stopped for a number of years, and now it became renewed industry around 2010, about 10 years ago, in reactivating these mines. So the main concern here was, well, if there was any kind of release, any kind of an accident because of a rainfall event or something, where was all that uranium, where it could go, because it could contaminate all these areas here. You see here where it says Bannister River intake. These are water intakes for different cities, okay, that take water from this river system for consumption. So here there was a committee that was formed and some consulting firms, and this is in the map here. You can see where this area, this is Virginia, and this is North Carolina, West Virginia is there. This is really mining country. This is where most of the coal mines are. But this particular area is drains, the main river here is the Bannister River. So one of the problems when you're trying to figure out how do you make an assessment of what the potential risk and of contaminating a given area with this economic activity is that you need to do a lot of data collection. So some of the data might be available, but some of the data might not be available, which is usually the case. So here we have river cross sections. We have sediment data, which is what we try to get, precipitation data, whether or not there are some hydrographs registered, if there are U.S. Geological Service gauging stations. And then what you need to have is the tailings characteristics. In other words, the tailings at the uranium mine operation, what are the characteristics of those? So once you have all that information, then with the help of modeling, you can analyze different hypothetical failure scenarios. So in this particular case, we're going to see that getting the data in itself was not that simple. So I was reminded that I need to use the mouse so that people that are on the video can actually see this, the cursor here. So here what we have if we look at this slide, this is an enlarged slide. You can see that all the uranium mining activity takes place in this area. So the mines are kind of across ways. This is the watershed of the Bannister River. Okay, so the Bannister River runs this way. You can see that it has reaches where it's meandering, has reaches where it has been straightened, and it keeps moving towards the ocean, basically, draining this way. And everything that you see in red here is the location of the former mining sites. So here you see a little purple circle. Not sure if the lights, if you can see well there, where I have the cursor. So that's the new uranium reserve that there was interest in renewing the contract, the lease, to start mining again. So here there was some cross-section information that came from FEMA studies, which is these arrows that you see here. So that means that there were cross-sections for the river that you could use in a model. And then there was some cross-sections in the area further downstream. Okay? So that's the physical information about the river system that drains. So the main concern here is, well, you start all this mining activity again, you reactivate the mines, the extraction of the ore, of the uranium, and if something happens, if there is a spill, how is that spill going to go down in the system through the river, and whether or not the spill is going to contaminate the water supply in that area. Hydrologic data, the hydrology. So here we can see another, the same map that we saw before, but in each one of these triangles here, okay, this tells you, as you move downstream, it tells you how the drainage area is growing. So up to that point, you're draining 281 square miles. By the time you come here, you have 363 square miles. You keep moving here, you have about 470, and so forth. So where you see the red triangles, which are not that many, this is the main location of a U.S. geological gauging station. But you can see that there are a lot of streams here, subbasins that contribute to the Bannister River, the main river, which is the thickest light blue line here. So there are some streams coming from the north, okay, and then there is other streams in the system. So here, mean annual precipitation is just over 1,000 millimeters, okay? So the total drainage area for the Bannister River is on the order of 1,550 square kilometers. So this gives you an idea of size. So one of the important aspects in all of this is that down here at the end of the system, right there is the so-called Kent Reservoir, and that's a reservoir that was built mainly for water supply. So here we have a view of one of the sub-watersheds. Okay, so the Bannister River is here. Okay, is the one that we just saw in the previous slide. So just south of it and coming to this point, there is this other sub-basin for the Dan River watershed. So this also brings a large amount of water that you have to take into account by the time you're trying to do a water budget, a hydrologic analysis at the end of it. So here we have an additional USGS gauging station, and at this particular location where we have the yellow triangle, hydrographs were developed for different flows. The same thing happened here. Wherever you see the yellow triangles, well, for each one of those, hydrographs for different return periods, different frequencies, were developed as part of the hydrologic analysis. So why is this area taken into account? Well, because this area comes, the Dan River comes down here at the very southern portion of the river system. So because it's coming all the way down here, it's bringing water also to Kent Reservoir. So there is the water that is going to be coming here, and then there is the water that is going to be coming here. And as far as what the impact is going to be here of any operations there, we have to take that into account in terms of a water budget. So there is another river on the northern part, the Roanoke River, and here you can see that this looks like a higher order stream, and this also brings water from the north, okay, and contributes to the main water supply reservoir that is here, this Kent Reservoir. So you can see where the location of the mines is, okay, so the main Bannister River watershed is here, but by the time the Dan River that comes from the north, the Roanoke River that comes from, the Dan River from the south, Roanoke from the north, they all merge at some point and go into the Bannister and go into this reservoir that we have here. So all the red dots that you see there, these are all former uranium mine sites, but also some of them could be reactivated at that particular point in time. So the size of all this is fairly large. So here you need to have all the information on the watersheds. You can see that for each one of them we have the drainage area, and here we have several peak flows that could result. This comes all from the hydrologic analysis. This gives you this is in cubic feet per second. Gives you an idea of the size of the flows that you can get. What is the basin lag time? Basically, what is the time it takes for the center of the precipitation to translate to the outlet? And these are some of the channel velocities that you have. So you have to do all this for all the subbasins that eventually contribute water to the Bannister River and to the Kent Reservoir. All that information needs to be available. So the idea is to develop hydrographs at different locations where we have the yellow triangles, all these different creeks for different return periods, and to have an idea what are the peak flows that you're going to have, so that then you can translate, you can route these hydrographs through the Bannister River and see if in the event of an accident or a failure in the system, how long it would take for sediment contaminated with uranium tailings to propagate. The next aspect that is important is the sediment and the water quality, okay? So here you can see this is a whole watershed. The Kent Reservoir is here, and you can see all these green dots are places where the U.S. Geological Survey has taken water quality data. So the U.S. Geological Survey, probably many of you know about this agency, but it's the agency that is in charge of measuring stream flow throughout the U.S. And also at many, many locations, they also measure sediment and they measure water quality. So depending on where you are, there is a larger density of stream flow gauges, but here you can see some of those gauges. And these are important because here you get parameters such as water temperature, specific conductivity, suspended sediment concentration, and then suspended sediment discharge. Bellload measurements are very, very rare unless you do that for a specific project during a short period of time. So here what you can see for the locations where there are measurements, this is for different values. For instance, the graph on the upper left, let's see, I think I lost the mouse. It is here now. Right about here, the upper left image, what you see here is flow discharge in the upper vertical. Those are values of Q in cubic feet per second. And then in the lower axis, you have suspended sediment concentration in milligrams per liter. So what you can see in most of them, on most of these graphs where you have measurements, that the periods of measurements are limited. You can also see a lot of scatter in the data. So you cannot see a very clear relationship here. There is a little bit of a trend, but in general, the measurements are very spotty and there is quite a bit of scatter. And part of that had to do that if you look at this table, the table that is here, the periods in which the measurements were taken are limited, and some of them were a long time ago, like this one, water temperature between 1950 and 86, and you have the same parameters in that period, but you don't necessarily have the same at all the stations and for the same length. So lack of data is a problem, but having some data. So this gives you an idea of what is the background concentration of suspended sediment. But the good thing is that during those periods of time, the uranium mine activity was taking place. So it gives you some data that is contemporary with the time of operation of the mines when they were active. Since there is very, very little information regarding grain size distribution, remember, for those of you that were here yesterday, we talked about grain size distribution, and this is why this is important. So this had to be estimated with a few samples taken from some of the streams, the floodplains, for each region, according to some data available from U.S. Department of Agriculture and the Soil Conservation Service lab. So you can tell by the shape of this, here we have grain size, here we have percentage finer by weight on the vertical, and this kind of gives you an idea that the material, at least the samples that they collected here, the sizes were fairly uniform because these size distributions are very, very much vertical. But as you can see, the information is limited. These are some of the streams, as you can see here. There is a department called the Virginia Department of Environmental Quality. So something that is very, very common these days, not now with the current administration, but in the past, the Environmental Protection Agency imposes water quality standards. So one of the things that need to be done for all the streams, particularly where you have agricultural areas or different type of economic activities, you have to conduct an analysis to determine the so-called TMDLs, and these are total maximum daily loads. So this is how much you can discharge into the stream in terms of nutrients, nitrates, phosphorus, fertilizers that you may be using in agricultural areas. Anything that is going to end up, when it rains, is going to wind up in a river, or if you have pig farms, any kind of feed farms, anything that you have to do with cattle, you have to get a permit in order to be able to discharge water. So one of the total maximum daily loads evaluated was for PCBs, polychlorinated biphenyls, and as well as mercury. Wherever you have mining activity, particularly of uranium, you are bound to find mercury. So what this part of the study had to do, this is very, very small here at the bottom, but there were total maximum daily load studies done here. And the segments that you see in yellow are segments that have problems with water quality standards. Okay? Another analysis, remember what we are trying to do, you're trying to develop a benchmark for the watershed, benchmark conditions, know the conditions of the watershed in general, so that this new, something happened, uranium mine activity, when it, I think we have just exceeded the total maximum daily load for the air conditioner. Okay, so because you're trying to develop a benchmark for what are the conditions in the watershed before a potential activity is going to start, another element that is important here is a survey of what the physical habitat is. Because what you're trying to do, in general, is know what kind of species you have on the watershed and whether or not they could be affected, or whether or not they have already been affected. So for this, you have to go and take advantage of the data that the EPA might have connected. And here you have, what you are trying to do is get an idea about sediment gradation curves for the Bannister and the Roanoke rivers, taking into account how the sediment is being sorted out through the watershed. So finally, we make it to the uranium mine tailings here. So when you get to this part and you're trying to do the evaluation, what you have is mainly evaluation from the past. So here we have a figure that essentially gives us grain sizes, typical grain size distributions for uranium tailings. So the curve goes the other way because in terms of grain size at the bottom, because here is a course, this is 100 millimeters on the left, and then here you have 1 times 10 to the minus 4 on the right, and then here we have percentage finer, 0 to 100%. So the coarser material is here, the finer material is here, and these are curves obtained with data from different uranium mining operations. This one from Wyoming, another one from Wyoming, 1979, 1980, and then from Colorado and Utah, you have some average curves here. So what you can see is that the tailings, by and large, in terms of size, they go from this value here, which is less than 2 millimeters. Everything is in the range of sand or finer. So we have a sieve number 10 there. This is the sieves that you use for sieving the material. And then here you go down, all the way down to about, I could say, on the order of 3 microns, 5 microns. So very fine material. So the range of silt and clay. The most important part is that what is the chemical composition of each one of those tailing sizes, grain sizes, which is the table that we have at the top here. So here you can see this is sands going from 75 microns to half millimeter, 500 microns. We have the slimes, which is the silt and clay, which is the second one here. This is the silt and clay rain size. And then we have the liquids, the leachates, what leaks seeps through uranium mine operations. So here what you can see is that there is quite a range of compounds and minerals in the chemical composition here. And then the other thing that you can see is what are the radioactive or radioactivity characteristics of these different chemicals that you have. Usually this type of mining operation, the material, the fluids that leach are very, very acid. So this is what can cause problems, basically, if it were to be released. But this is not necessarily what is there, but it's information that you can have. Something going on? Okay. So here, up to that point, when this study, this evaluation, to obtain a permit or authorization to, up to that point, 2008, there have been few studies about or compilations of failures of tailing dams. So this was a paper published by Rico and collaborators in 2008. And here you can see this table with mines that have tailing mines or tailing dams, rather that had failed all over the world, literally, the date of the failure, and then here you have the type of dam, the height of the dam, the impounded volume. This is in millions, okay, of cubic meters. That's the volume of tailings that you have behind the dam. These are the run-out distances that people have observed. And this is the so-called dam factor. And the dam factor essentially is if you have a, yes, so if we have a tailings dam that has been built like that, and here we have the sediment that has accumulated over time. So you keep building this up and filling it up with new layers of material. And this structure has a certain height. This is the same for a water dam as well. And in here, we have a certain volume of tailings. It could be volume of water too if this were clear water. But this is all filling up with the sediments and you're building this up. So the dam factor, the parameter that we see here in this column, is the volume of fluid and sediments that we have here, and the definition of the dam factor is essentially the product of the height of the structure, the height of the dam, times the volume of the fluid sediment mixture that you have there, because obviously here you have liquid and you have sediments, you have tailings as well. So this factor is a factor that you see here in this column, and as we are going to see today, that's an important factor in the analysis. So right here, what you see in the last column, we have the run-out distance, which is how far, when these tailing dams fail, how far did the material move, how far downstream. And here is the volume of material that was released. And what you can see is that there is a difference between the impounded volume, what you have behind the dam, and the amount of material that is actually released, okay? And that, as we are going to see throughout the morning, that ratio becomes an important factor, okay? So here you can see that there are, the first dam up there is the one in Zimbabwe, South Africa, Romania, Chile, US. There are a few in Chile, a few in the US. This is a famous case, is Gypsum Tailings Dam. And then Hokkaido, there is one in the 80s here in Brazil. So this was up to 2008. Obviously, there have been more failures since then. This is a case that has been studied a lot, Los Frailes in Spain, 1998. But this is the information that is available to have an idea of, well, when this failure happened, how much material was released. We are going to see today there have been some updates regarding this. So, at that time, remember that this study was done in 2010. The reason why I'm showing you this is because I mentioned it before, and I wanted to see, for you to see, what do you have to do in terms of the scenarios that you need to analyze to get a project to move forward and minimize any potential impact. So based on 29 historic failings, these authors, Rico et al., they developed some very, very simple relationships. So once you have the size of the dam and the volume, these relationships can be used as an approximation to estimate what is the volume that could be released downstream in case of an accident, and roughly what would be the round-out distance. So here what you can see, we have the relationship between the peak discharge and the dam factor, okay, that we mentioned before, the product of the height over the impounded volume. And here you see values of peak discharge, Qmax, what is the maximum flow that can come out of these tailing dams based on observations. And you can see that the data shows scatter, but on the other hand, you have a mixture of constructed dams and then landslide dams that basically the ones that we mentioned the first day that they could form due to a landslide. And you can see that there is a trend. So there are different equations that you can use. One for this one, the constructed dams. So basically, the maximum peak discharge scales with the square root of the dam factor, which is a product of the height of the structure and the impounded volume. So you can see that these values can be quite large. This is 1, 3, 10, 100. This is 1,000, 10,000. This is in cubic meters per second. So the flows can be fairly large. So this was one of the relationship available from Rico et al. This one shows you, this is the impounded volume, which is the volume you have impounded behind the dam, versus the outflow volume. Actually, what was the real volume of material that came out of tailings and liquid and water. So here you can also develop another relationship. And this is obviously all empirical, but the R-square value is not too bad. It's on the order of 0.86. We are going to see that there are newer relationships for this. There is more recent work that has been developed. But you can develop some kind of an envelope. So you can say, well, if you had a perfect line at 45 degrees here, it would mean that the volume that you have impounded has been released, 100% of that volume. So you can see that would be this line here. So if we move down from there, this is what people observe, that you're actually releasing a little bit less or less than what you have impounded. So there is material being left behind. And this is a very important, I wouldn't call it parameter, but a very important outcome to have an idea of how far this is going to go. So here we have the outflow volume now, how much came after the failure of the tailing dam, came out of it, and what is the run-out distance. So you can see that some of those values are on the order of 100 kilometers up to the point with the failures that had taken place. So what do you do with all this information? Well, it gives you an idea of what could happen. On the other hand, we have to be cognizant of the fact that this is just empirical information. Here there is no information of what is the characteristic of the river where all these tailings are going, or what is happening downstream from the tailing dams, of all this data. This is just very primitive data, if you want. This one is useful too, because this is the run-out distance, how far the tailings are going to go versus the dam factor. So here you can see that the scatter is much larger than what we saw before, but still these authors, they put together some very simple empirical relationships. We are going to see that very recently, as 2018, researchers at the University of Columbia in New York City, they have tried to update all these relations. Okay? Here is an example. Yeah. All I know is I don't remember off the top of my head. I mean, what has been in the news that the volume that was released, probably somebody has estimated that by now, I imagine, right? Yeah, do you want the microphone? Yeah, Marcos here might know.
My name is Marcos. I introduced myself today, okay? No, just few points about the Brumadinho. The media showed 12 million cubic meters, but actually it was the total stored volume there. But as we saw, Professor Garcia showed, it's not total volume that comes out of the, in general, it's 1/3, more or less 1/3 volume. So we guess more or less 1/3, 4 or maybe 5 million there, but it's a guess. So far, I haven't seen official data about this, but it's more or less, I guess, 5 million.
Yeah.
My question is related also to the distance. So in some points, you have here some experiments. All experiments, they have some uncertainty, because how can you measure the real distance of the concentration traveling? That means you have some NOR protocol
No, but
to compare?
I think you missed this one. This was all this data, these points that you see there, these researchers, remember this was 2008. Now we have new publications, but all this came from this table. They selected 29 of these, which is what you see there at the end. And then they tried to use this data to develop these empirical relations. So, yeah, this is a very approximate analysis, but it gives you an idea of what can happen. So, the main take-home here is that yes, this gives you an idea about the range of peak discharge as a function of the dam factor. And probably what is lacking the most here is the fact that the run-out distance is going to be affected not just by the volume of material that you are releasing, but also by the elevation, by the potential energy that you have, depending on where the tailing dams is located. So it's not the same to be at 100 meters above mean sea level than to be at 1,000 meters above mean sea level. And the topography, right? So the topography, the geomorphology, downstream, all these factors are going to have an impact. So all that information is not contained here. Here they just went and say, well, this got this far downstream, this was the flow that was estimated. And if you look at the literature on dam break analysis for clear water, yeah, people have been trying to make approximations like this for a long, long time. So run-out distance, it gives you an idea. It doesn't mean that if you release this volume, you're going to reach always that distance. The tailing is also going to be different. So notice that here, what is implicit in all these empirical relations, and these fits, is the fact that you don't really know what is the nature of the tailings. They cannot all be the same and behave the same. So here are more bulk parameters trying to characterize what's going on. But nevertheless, they are useful because they give you an idea of the range of where things could be. This is an example that came out on this analysis, and this is for these tailing dams in Spain. Was a lead zinc dam. This was 1998. It's a case that was studied quite a bit, and what you can see here, what is interesting, is this a hydrograph that was taken at a certain distance, about 11 kilometers downstream of where the tailing dams failed, okay, April 25, 1998. And the hydrograph that they recorded there, first the water got there, and then sometime later, a few hours later, there was a tailings wave basically reaching that particular location. And of course, this is just one case, but it goes to show that the complexity of the phenomenon, because it's not like everything is moving together, the water runs away. So we have seen this phenomenon in density flows, in turbidity currents, where the front tries to get away from the body of the flow. And some of it has to do with the fact that water gets underneath, in the case of submarine flows, gets underneath the front, and the front kind of takes off. So if you have a wave, if we have a wave that is advancing, okay, and is moving that way, and this might be both sediment, is a mixture, plus water, somehow the water is going to find a way to get to the front of the front. And a lot of it has to do with the weight that you have here that basically squeezes the water. The water tries to get ahead. So the water, there is going to be a frontal area that may be more water plus fine sediment that gets ahead of the rest. So there is, as the slope is changing, the transport capacity of the flow goes down. Some material might be deposited along the bottom. So at that particular location, you didn't make it all the way down there with all the tailings or the sediments that were released at the time of the accident. So, but it's an interesting example, one that people have used. So what people did for, in this particular case, was try to put together a model that would allow them to analyze what could happen in the case of an accident, of a failure. So we have here hydrodynamics, sediment transport. The case that was analyzed here was a dilute case in the sense that they want to look in a mass movement, but here we have a hydrodynamic model for water and sediment mixture, a sediment transport model to simulate suspended load and bed load, okay? And then a morphologic model to simulate changes in bed elevation. We mentioned the Exner equation yesterday for sediment mass conservation, and we'll come back to that. And then you need to have some way to look at the transport and fate of the radionuclides that you might have either in solution in the suspended sediments or that end up in the deposited sediments. So all these things were accounted for. So what were the objectives of the analysis? The objectives of the analysis were, in the case of a failure of a contaminant cell, so you have these cells where you put the tailings, what amount of radionuclide contaminated sediment could be released, and how much water could be released, and how much of that could reach this water supply reservoir at the end of the system, the care reservoirs that we show at the beginning. So the potential scenarios could be a flow caused by extreme precipitation that might have triggered overtopping, for instance, of one of the cells containing tailings. Another case could be continuous high flow events, not necessarily one rainfall event, but the fact that you can have a lot of water on the upper watershed, and the fact that these mining operations are very close to a stream, yeah, flow could go over bank and could cause trouble. And what would be the potential increase in background radiation levels and other contaminants? So here the main worry was that if an accident would happen, even though a small amount might be released, all this could go all the way down and accumulate in the reservoir that has a main water supply. But the other problem could be that all the other water intakes in the system that we saw at the beginning let me see if I can. There is a risk always of doing this, that we don't come back. So remember what we're trying to do here. If we go back to this slide, what we are trying to do is that to figure out if something happens here and there is a release, how is all this going to get routed? It's going to get transported, sediment, tailings, radionuclides. How is this going to move through the system and get to this reservoir here that is very important. That's the whole idea of the exercise. So the first component of the modeling, or for the modeling, is a one-dimensional hydrodynamic model. So these are like a Sediment type of model. These are the Sediment equation we have here. Continuity, conservation of water volume, and the Q, the reason why you have a Q here is because it could be lateral inflow coming in. And here we have the momentum conservation equation. So instead of working with velocities, the equation is written to work with Q, with flow discharge, and cross-sectional area. So this divided by this is basically the velocity. So we have the typical terms here: temporal variation, convective term, the pressure term, and then here we have the difference between the friction slope and the slope of the channel. And the friction slope is estimated this way. This is what we call a conveyance factor for a river or a stream or a canal, which is simply made up of the product of cross-sectional area, hydraulic radius to the 2/3, and then here we have Manning-Sen. So you need some kind of model to route the water, basically. This is what we would call a 1D hydrodynamic model. The second one, the second model, is for sediment transport. And at that in this particular case, the agency that was doing this, the Commonwealth of Virginia, have hired a company that in turn have hired researchers from University of Mississippi. So the models that we're using were the models that, this was a group of Professor Altinakar at University of Mississippi in Oxford. So these models respond to that. You could use other models, but this basically is a sediment transport model, 1D, that also works with flow discharge. The main difference with other models that this one was done for different fractions of sizes, and using the so-called equilibrium approach, which is for each fraction, what is the equilibrium transport rate of sediment that you can move for a given liquid flow discharge. So what the model is doing constantly is comparing the sediment transport capacity of the river, which is this QT asterisk K, which is this value there, is comparing that value with the actual sediment transport that the model says that is taking place. Okay, so you get this from a transport relation, basically, a sediment transport relation, and you get this from the model. This is what you're modeling through. So if this is equal to this, these two are equal, the sediment transport capacity and what you're actually transporting for a given flow discharge, obviously the flow is in equilibrium. Then you can have inflow of sediment, lateral inflow of sediment, and this is simply a length of non-equilibrium sediment transport. So there's going to be reaches in which there is an equilibrium between what the flow can transport and what the flow is actually transporting in terms of sediment. So when those two are the same, this term becomes 0, but when those two are not the same, then you have a length of the river where you have non-equilibrium. One important factor here is that this sediment transport capacity is a transport rate for each class size of sediment. You need to multiply the flow discharge by the fraction of material that you have corresponding to each side. So we are talking about mainly bed material, what we are talking about here that is being that is being moved. So there are a bunch of transport relations. This is the excellent equation, but instead of writing it the way we saw it yesterday, it's simply a sediment mass balance equation where we have porosity here. We have basically the portion of the bed, the area of the bed that is changing as a function of time, and it's changing depending on whether or not these two factors are the same or they are different. The flow discharge, the sediment transport discharge, and the equilibrium sediment transport discharge. So this term is the same term, essentially, that is in the one-dimensional sediment transport model. So this is what the flow is moving, and this term here is communicating with the bed, essentially. Yes? See, that's concentration of sediment. Yeah, I don't think it's written, but it's concentration. Yeah, so it's cross-sectional area times concentration. It tells by volume. It tells you of that cross-sectional area per unit length, which is a volume, how much is sediment that is being moved. Yeah. So this is for the bed. You can call it bed erosion, bed deposition. And then you need to have an equation for the radionuclides themselves that can be going in suspension. And this is where it gets really tricky because, well, how do you know how much of this is going to go into the river? Nobody really knows. But that's why you do this analysis, this failure analysis. So this is essentially the sediment advection diffusion type of equation for suspended material. So you can see that you have in 2 dimensions here. And what you are assuming is that the contaminant may have a fall velocity if it's attached to particles. So the contaminant is fine enough to follow the flow in all directions, but in the vertical, it has what we call a slip velocity. So this is a concentration of contaminant being advected by the flow field, velocity in the main direction, in the lateral direction, and here you have the concentrations. And these are diffusion terms, okay, that we have there. This is a total loading, STB, and you can have transport of this in 2 and 3 directions, as we see here. So, what's the main purpose of this exercise again? Well, if there is a certain loading of radionuclides that enter the system at the location of the spill or the failure, what have you, can we actually track them? And I'm going to tell you in a second what these units are. So, when we put the whole information together, some areas didn't have all the data. So they had to go back and get some satellite images and try to rebuild, because remember at the beginning I showed you the areas where we had cross sections, but there were a lot of bridges. We need to get reservoir geometry. There is a lot of office work that needs to be done to generate these digital elevation maps. And I would argue that in this day and age, any analysis of tailing dam failures, digital elevation maps are going to become crucial to get the whole information about the geomorphic information, downstream information about the structure itself before and after the accident and how things look like. This is crucial, okay? But you need it to complete the information that you don't have. Unfortunately, what happens sometimes, not in this case because this was being done to figure out what could happen, you don't do the digital elevation map before things happen. So if you try to do it after it happened, well, now everything has changed in the terrain. So the trick is to actually, if you have a site and you know that there is potential for failure, well, get a digital elevation map so that you can develop all the background information that you need for these models. This was the case of the Bannister River. Also, we have to recognize that in the last 10, 15 years, satellite information has become more and more readily available, and before we didn't have that to get all this information. So, two types of simulations, short-term, long-term simulations. These ones are focusing on the transport and rate of radionuclides released due to a failure of a contaminant cell, let's say during a storm event. And you have different scenarios analyzed, combining different release quantities, release durations, and different hydrologic conditions. So you have the model, presumably you calibrated the model with existing data, at least the hydrologic component and the hydraulic component, and then you can do this type of simulations. The other type of simulation, more long-term, is that it is possible that some of the radionuclides that get released, they don't reach the reservoir. Well, where do they go? These sediments remain in the channel and in the floodplain, and they obviously are going to be a source of radionuclides in the future. So you might lose them during the event that mobilized them when they were spilled. They may deposit. Well, that doesn't mean that they're going to stay there forever on the bottom, deposited. They may get remobilized later on. So the short-term simulations then can be used, and the 10% annual chance flat, okay, that could be like, a 10-year flat, are used to test the model. What do we use for the rest of the things in terms of suspended sediment loads? Well, these are all the records that we have to collect. So this gives you an idea that you need to get a lot of information if you're going to do this. And this is what we saw before. We have the suspended sediment loads. We get that from the USGS, the grain size distribution. And this information is important. The uranium mill tailings have an activity of about 130 BQ per gram. So this BQ is an international unit of radioactivity, which has a funny name, becquerel, and this is the way this is measured, okay? This, I think, is the most tenuous part of the analysis, because you don't know really how much you're going to be releasing. And there was a lot of work in the 70s and 80s in the US by different groups looking at radionuclide transport, particularly associated with nuclear power plants, not with mining. And that's when some of these models were developed. But what you need to figure out is that you have to assume something about the grade of radioactivity that those radionuclides that are going to get released, in this hypothetical case, they are going to have. So this is something that has to be done by someone that has obviously experience on this type of contamination problem. Here, what we have, okay, is the exchange between the solid and the liquid phase modeled or simulated through this absorption-desorption process. So the whole idea of this exercise is to use, this is percentage of total radioactivity in suspended sediments in this axis, and here there is a distribution coefficient, this KD in cubic meters per kilogram, and here you have different values of suspended sediment concentration. So what is that coefficient KD? That coefficient KD is a ratio between the amount of contaminant sorbed by the sediment to the amount of contaminant left in solution in the water, basically. And you don't know exactly how much that is. So the only way to get to this is to do a modeling exercise and change this parameter, okay, to look at the exchange between the solid and the liquid phase that can be happening as the contaminant is being transported, basically. So here you have estimates of that coefficient KD, this partition coefficient, of radionuclides in natural water with an emphasis in oxidizing conditions. See, this is more chemistry, water chemistry, but this is what people know about salty water and this is what people know about fresh water. But you can see that there is quite a range of the value of this coefficient. So you're going to have to look for what is the element that you're dealing with in the first column and then choose a range of values. This is the part that we know the most, which is, well, you calibrate the hydrodynamic model with the roughness, you validate the model, and then this is the part that gets challenging again because you need to choose some transport relation. If we had to do this again, well, this probably would be done differently these days, but these are some of the sediment transport formulas available at that time that the University of Mississippi model accepted and could be used. The idea is to try to find a formula that is representative of the sediment transport rates that have been measured. So finally, the final exercise, the assessment approach to figure out what will happen. We set up the model, calibration of the model using steady state discharges, for which you know what the USGS gauges are giving you, short-term simulations to assess the level of contamination due to radionuclides and selected toxic contaminants that might be present in this particular case, long-term simulations to assess the effect of the contaminated sediments on the water quality of this reservoir. In other words, there is a cumulative effect. So water reservoirs become repositories of sediment over time. So they cannot tell you, if you take sediment cores, they cannot tell you the history of the economic and human activity in a watershed because they collect the sediments that came from different locations of the watershed. So the geochemistry of the sediment tells you a lot too. That's why you need a long-term simulation. Because it might look like, well, yeah, depending on the amount that the spill, this might not look like much. But if there are several spills, or there are a large spill and then many flood events that keep mobilizing the radionuclides and the sediments, that can be a problem. You do a sensitivity analysis, and that means changing the boundary conditions, but also changes the value of the parameters, like the parameter, the KD. We didn't mention it too, but there are diffusion coefficients, there are dispersion coefficients, there are things that we need to have to run these models. So we do an assessment of radionuclide contamination in the reservoir, both for short-term and long-term, and then we can reach some kind of conclusion and say, well, if this happens, we are going to have this level of impact. So the agencies that need to authorize the reactivation of the uranium mine operations or the authorization to start new ones, new reserves, they need to have some kind of analysis conducted, study analysis, before that is essentially done. Otherwise, there is no control. Anybody can go up there and start mining and so forth. I don't think that the uranium mines were reactivated because this depends a lot on the price of mining and the cost of processing the uranium. So this is a bit like oil. Depending on the price of oil, things go one way or they go the other. But at least it gives you an idea of how this is done. This, for the reservoir, usually what you do in this type of analysis is what we call a screening model methodology. You try to estimate like an annual average, how much is going to make it to the reservoir, how many toxic contaminants you're going to have, and then you need all the information about the lake. Depending on the size of the lake might stratify, depending on the time of the year, due to temperature, there are a number of factors. But you can assume that these concentrations of the radionuclides can be constant or uniformly distributed in the water column as they enter the reservoir. All you are trying to find out is how the concentration of radionuclide in the lake is going to change as a function of time. That's the most important parameter. And this is all based on what you see there. This, sometimes you don't pay a lot of attention, but is the most important part. Because sometimes even if you have a bad model, by repeating and doing many exercises, you can learn about the response of the system and to changes in different parameters, okay? So you might want to change the modeling parameters, the sediment transport formulas that you use, and look at the relative impact of doing these changes. That's the advantage of having the model. And then you might address, uncertainties that you're going to have to a choice of particular model. Sometimes people are very comfortable with a model and they, because they have a lot of experience with this. So they put a lot of faith in it, but that doesn't mean that, number one, that there is another way of doing it and that the model is always right. So it's important to be flexible. And then to do Monte Carlo simulations. You study the uncertainty by changing parameters and looking at the outcome that you get and repeating this several times. So we are going to end with that, and I'm sure that you have questions, at least for this first part of the morning session. The next talk is going to expand on this, because the next one is based on more recent work that use an extension of these empirical curves that we have seen now, and it might be of interest to you. So I think what we can do is take a quick break. I was told by Mario that we need to finish by 11:30, I think, or maybe a few minutes earlier. So do you want to take a break? I said, do you want to take a break? Do we have a coffee outside or? Okay, let's take a quick break. 10 minutes and we come back.